Hi, my name is Rune Andre Haugen. I'm an industrial PhD candidate at USN and working at Kongsberg Defense and Aerospace. The title of my project is Exploring Probabilities of Detecting Emergent Behavior in Systems Integration Testing by use of experimental design and Bayesian statistical inference. The goal of my project is to create a model that we can play with to validate to what extent the company is able to detect a given set of emergent behaviors. What I want to go through in this presentation is to look at the problem statement, the research questions, the emergent behaviors that I have looked at, the model, the input and output, the results, and the conclusion. This will take about 20 minutes, and then we have 10 minutes for questions. Here you see a picture of a autonomous underwater vehicle system. That is the case I have used in this project. I can show you a short video of this to sort of get in the mood. So I'll run this. So for my case, I want to look at how this AUV can capture images of the seabed. And what's the problem with testing this? Generally, we lack coverage on system level because testing, at least realistic testing on that level, is very costly. And this lack in test coverage give rise to these so-called emergent behaviors. That is really behaviors occurring at system level that cannot directly be traced back to subsystems. It can be both expected and unexpected, desired and undesired types of behaviors. And this is a highly debated term throughout the years, at least dated back to this guy, the famous Greek philosopher Aristotle, who said something like the whole being greater than the sum of its parts. Further, the company is performing system integration testing based on a lot of manual operations. So this becomes time-consuming as well as costly. The main bottleneck being that analysts don't have time to analyze the available test results. Findings from the company show that on average we analyze around 10% of available test results. And among these, 20% of the tests contain different types of errors. And among these, 20% contain what we call behavior-related errors. That has to do with undesired behaviors of the system. Also, the company is testing too much sunny day scenarios compared to rainy day scenarios, I believe. So we aren't at the place where we really can detect sufficiently these behaviors to be able to analyze them and understand them. So my research questions are these. the main question being, how well is the company able to detect a given set of emergent behaviors? And sub-questions being, what is the probability of the company detecting this given set of behaviors with the current way we do testing? And how much can we increase the detection of these behaviors in an alternative test regime? I've looked at 4 different types of emergent behaviors. The first one being planning failure, which has to do with the map data we use for planning missions, where we will go and photograph the seabed. And this data has areas with lacking information. And these areas could lead to planning failure, depending on the quality of the map, more or less of these areas. The second one being fuel exceeded due to the complex picture of ocean currents that we aren't able to plan for in an optimal way. We might end up in a situation where we will meet more sort of head currents than we have planned for, using more fuel than we anticipate, and run out of fuel before we have finished the mission. The third one being photo quality degradation, which can occur if we are traveling over rocky terrain, over ridges with the steep slopes, so that the camera tilt angle and opening angle aren't able to cover all of the seabed area. And the fourth being photo coverage deviation, that has to do with navigation quality. If the main navigation system fails in some way, or are in some way not fully operational, and we have to rely on the backup inertial navigation system only, we will drift from the planned trajectory and not cover the area we set out to do. So these emergent behavior types are input to the model in my case, and these behaviors are triggered by different scenario factors. So I've set up 4 different factors as input to the model, with 2 levels on each factor being high or low. And we can look at the first one, map quality. That has to do with the failure type 1, the planning failure. Different quality in the map, with more or less of this lacking data areas, will trigger the planning failure with different probabilities. The real-world environmental data, being how much the ocean currents are varying from what we have planned for, impacts the amount of fuel we use and the probability of getting this fuel exceeded behavior. The map delta height, being the height difference in the map, and the map quality again, impacts the photo quality degradation. How often we get into the situation with these steep ridges that we cannot cover sufficiently. And the last one being the photo coverage deviation. That has to do with navigation quality. If we will lose the main navigation system and drift away from the planned trajectory or not. The next input to the model is the different test regimes that I want to compare. The first one being the current way we do testing that I've called the sunny day regime, where we test most on test case type 1, where we have the factors on the levels at the optimum level regarding ensuring successful tests, minimizing the errors, so we won't get much detections in this setup. And we only test a few instances of other combinations, sort of just to look at the isolated effects of changing factor C from low to high, changing factor B from low to high, etc. So I want to compare this with an alternative, more balanced test regime that many of you know as a two-factor full factorial design, where we have 4 factors, 2 levels. We get 16 possible combinations, and I want to run all this equal amount of times. Third test regime I've called maximized, because here I'm interested in maximizing the detection rate of these behaviors in question. And as you can see from the table, there's one case that is really triggering the behaviors at their maximum probabilities. I'll come back to these probabilities in the next slides. So here I only run this test case all the time. The same total number as for the other test regimes to compare them. Then we have input in expert knowledge from the company, the experts, their experience, their gut feeling, their engineering judgment, whatever you would call it, sort of a hypothesis for what we believe to be the probability of detecting these different behaviors. Then we can take data from our company test database as input. Like when we get the behavior F1, the planning failure, how much do we then have factor D that impacts this failure on high and low level? So 10% at high level, 90% at low level. Further, we can look at the portion of tests run at each factor level overall. So we run 98% of the tests with factor D at high level and just 2% with factor D at low level. And then we have enough data to be able to use Bayes' theorem to calculate the resulting probabilities given the significant factor levels that trigger these behaviors. And I believe this Bayes' theorem is a really powerful tool, because we can then combine all the knowledge and all the data we have into a resulting probability. So these are the numbers that you saw in the previous table. Then we developed a formula to calculate the probability of the different behavior types in a given test regime. And this formula tells us that it's really just dependent on this last expression how much we get of behavior 1 in a given test regime. So for F1, it depends in the test regime how much we run with factor D at high level compared to low level. If we set this to 0 or 1, we will get the lower and upper bound of this F1 behavior. And if we multiply that by the amount of tests we run, we get the amount of detections. And if we do this for all the behaviors, we sort of get our playground, the limits we have to stay within, no matter how we design the test regime. So I've calculated the probabilities and the detections of the different behaviors in the specific test regimes that I have used. As you can see in this table, and test regime 3, which is the maximized test regime, has got the same numbers as the upper bound, while number 1 and 2 are somewhere in between the lower and upper bound. Number 1 being quite close to the lower bound, actually. Visualized in the graph to the right here, you can see that test regime 1 being the green pillars, they barely show. So we get almost no detections, there's almost no probability of detecting these behaviors in that test regime. The blue, test regime 2, seems to be more promising, and of course the yellow is the best one, which maximizes the probabilities. Same graph regarding the detections show the same principle. It's just nice to see both the probabilities and the actual detections we get when running a certain amount of tests. And on this, in this table to the left, we can see the relative frequencies to compare the different test regimes. And we see that test regime 1 gives low detection rate. I believe this is too low for us to get significant amount of data to analyze the behaviors and understand them. Test regime 2 might be an okay option, triggering to at least some extent, while test regime 3 seems to be the best option, maximizing the detections. But there's always a but. I've not yet incorporated the uncertainties in these numbers, so there's some risk related to this design of test regime 3. It might not give us this highest score after all, so I believe it's a safer way to go with test regime 2, at least for now. So to sum up the results, they show that the company could absolutely benefit from changing to an alternative test regime in the sense of detecting enough of these emergent behaviors. The current way we do testing does not seem to trigger these behaviors sufficiently to be able to understand them. But an alternative test regime seems to be able to trigger them sufficiently. I think a combination of this test regime is the best way forward, because there's different needs to different types of testing. Like integration testing, we want to detect these inherent emergent behaviors of the system to be able to deal with them. But for verification testing, we really want the tests to succeed to to show the customer that this works. So further work is needed to set up a test regime or different test regimes to meet all these different needs. Okay, I guess that's it. Are there any questions? Okay, thank you.